In this video, I'll give a very easy to understand and intuitive explanation of a very popular machine learning algorithm called k-means clustering. Now, clustering is a very useful machine learning algorithm which has a wide variety of use cases. And the best part is that it belongs from the class of unsupervised machine learning algorithms, which means you do not need training labels to create these machine learning models and get some benefit out of it. Now, to explain k-means clustering, let's try to look at some real life scenario. Let's say you work in a marketing department of a superstore and you want to introduce some personalization to the email campaigns or direct mail marketing campaigns, and you want to segment your customers into different categories so that you could create those emails much more personalized rather than just sending the same kind of emails to everyone. Now, of course, if it is a real life application, you'll be looking at a lot of factors, but to keep things simple, let's say you just are looking at two data points. One is that what is the age of the customer and how much they have spent in the last 1 year in your store. And of course, based on that, you'll have some tabular data which will give you the value of these two columns for each of the customer you have. Now, in order to give an intuitive explanation of it, let me draw some sample data point on a graph so that you can visually see what is happening there. So let's say on y-axis, I have the age, and then on x-axis, I have how much the customer has spent. So spend is on x-axis and then age is on y-axis. And let's say when you plot all these points on this graph, it looks something like this. So you have 2, 3 points here, and then you have 2, 3 points here, and then you have 2, 3 points here. Now, when you visually look at it, you can definitely see that there are 3 clusters here. But that is only possible because you are looking at 2-dimensional data, because you just have these 2 dimensions here. If you had more than 2 dimensions, even 3, you still might be able to visualize. But once you have 5, 10, 100 dimensions, and then there is no way that you could visually look at the data. So that is why machine learning algorithms like this come in handy, because the math what we see applies to 2 dimensions can also apply to 100 dimensions, even 1000 dimensions. Let me write down as I go along what are the steps we'll be performing for this model. So the first step is that we have to decide on the number of clusters. Now, this is the biggest limitation of this model, because if we do not know what the underlying data distribution look like and we have no way of visualizing it when we are dealing with a lot of dimensions, how can we tell that what is the right number of clusters? So this is the biggest limitation of this model. We'll see shortly one trick we use to find out what is the right number of clusters, but let's say in this case that the number of clusters is 3, and which means that this value of k here is 3. So once we have decided on the number of clusters, the second step of this machine learning algorithm is that we initialize the centroids. And for that, we randomly pick 3 data points from this and initialize them as different clusters. So let's say since our k value is 3, we'll be picking 3 random data points from this and use them as our centroids for our 3 clusters. Let me use 3 different colors so that you could visually see what's going on here. Now let's sort of take a worst case scenario. Let's say we pick these 3 as the centroids for these 3 clusters. So this is my green cluster centroid, this is my blue one, and this is my red cluster centroid. Now what we'll do is that for each of these data points, we'll measure their distance from each of these and then decide which cluster they should be assigned to. So even for this, we'll compare it against the distance from itself, and then this one, and then this one. And of course, for these 3, they are already at the centroids of their clusters. They'll stay like this. But for these data points, we'll measure their distance from this thing, and then this one, and then this one. And since blue is the nearest from these 4 data points, they will initially be assigned to this blue cluster. And when we look at all of these data points, and for each of these, we'll measure the distance from this one, and then this one, and then this one. This one again might be assigned to blue, but this one, since it might be near the red one, it will be assigned to the red cluster. And this was our step number 3, which was assign clusters, which we just did. Now the fourth step in this process is that we have to move the centroid. Now what is the centroid? Centroid is the central point for each of the cluster. When we initialize the centroid, we just picked random 3 numbers and we initialize them there. But now it's time for them to move. How would we move it? For each of the clusters, let's take this blue cluster. So it has 1, 2, 3, 4, 5, 6, 7 points in it. What is the average value of age? And we'll get some point. Let's say we get 4.7. And then what is the average value of spend for these 7 customers? And let's say we get something which is $68. And so that would be the mean value of these 7 customers. And let's say that point is somewhere here. So this is our new centroid. Let me say centroid 1 for the blue dots. Let's do the same exercise for red. So red has 2 points. And when we take the average value of these, let's say we get somewhere here. This is the new centroid of red points, and let me say it 1 because this is the first time we are calculating the centroid. And for green points, since it is only 1 point, it will remain here anyway. So it will stay like this. Now this step number 3 and 4, we have to repeat them again and again till we see that there is no movement anymore of the centroids. Moving back to assign cluster step, now we have to again assign clusters. Now when we assign these clusters, they'll again be blue because their nearest point is this centroid of blue. So let me again, so these will again be blue. How about this one? Since now it has another candidate, it could be blue, which is here, or it could be red, which is here. I think the distribution will still stay the same because it is still near this blue point and this is still near this blue point. However, this will still remain red. But these points, since they are now near green, so their cluster assignment will change. They will become green because their distance from this, and this, when we compare it, it is near green. So they will become green. Okay, so we assign the clusters, we again move the centroids. These 6 points we have for the blue cluster. And since there are more blue points here, this centroid will be pushed somewhere here, near them. So let's say this is the second assignment of the blue cluster. Now for red, there is only 1 point which has the red cluster assignment. And when we take the average of it, this itself will become red centroid. Since all of these 3 are green, so its centroid will be somewhere in between these. So it becomes its centroid. And the number I've written 1, 2, it's the second iteration of this. Cool. Now again, we have moved the centroid. Now let's go back to step 3 again and then assign the clusters again. Now let's see what happens now. When we look at blue ones and take its distance from this thing, and this thing, of course they're all near blue, so they will still stay blue. When we look at these ones, they are very near the centroid of the second one, so they will become red. And when we look at these, since they are again very near the green one, so they will still stay green. Now we again go back to this third step, which is we move the centroid. So the centroid for blue one, since these are the 4 points, it becomes like this. And for red one, it becomes in the middle of it. And for green one, it will still stay the same. And now the solution has converged. Now it doesn't matter how many times you move again, these centroids, they will not move again. That is how we know that we have converged, and hence that is the 5th point, which is we have finished when we converge. So this is a 5-step process which we have to take to identify that what are the k number of clusters present in the data. Since we just 2 features here, because it is visually easy to understand, it is applicable and can be expanded to as many dimensions as we want. Now coming back to the question of how do we know what is the right number of clusters when we cannot visualize the data, we use a very neat trick. It is called elbow method. Let me show what it means. So we do a plot like this, where on x-axis we have number of clusters, and on y-axis we track something which is called WCSS. It basically means within cluster sum of squares. The basic idea between WCSS is that, let's say if this is our cluster and this is our centroid, then for each of these data points we'll measure the distance from this, all of them, and this will give us some number. So let's say this is 3, this is 4, this is 2, this is 1, this is etc. So as the name applies, it is sum of squares. First we take square of all of these and then we sum them up, and that gives us a number. Let's say it says 68. Now that is the value of our WCSS. It indicates the total error present in this cluster. If all these data points were located on the centroid, then this WCSS would be 0. If they are very far away from the centroid, then this WCSS would be a very large number, which we are trying to capture here. So as on the x-axis we have number of clusters starting from 1 all the way to going to maximum clusters we can build, what we would see is that when we just have one cluster, which is going back to this example, let's say if all of this is under one cluster, we'll see that the centroid would be somewhere here, and then the distance from each of the cluster would be very high. So our WCSS would be a very large number, let's say somewhere like this. Now when we create two clusters, let's say if we were to take two clusters here, it will probably become something like this. They will go to the one class, and then this will go to the other class, and its centroid would be somewhere here, and its centroid would be somewhere here. We'll see that the error for this one would be small, but for this one will be bigger. So it'll still be higher than 3 clusters, but still relatively less as compared to one cluster. So we'll see the error will go down. And for as we create 3 clusters, it again goes down, and then it will keep going down. It will never go up, because as you approach infinity here, let's say if you had 10 data points here and you create 10 number of clusters, then for each of the data point, that point in itself would be its centroid, and its distance from that would be 0. So as the number of clusters approaches number of data points, we see that the error, which is WCSS, it approaches 0. So we'll see that it will eventually approach 0. But in real life, when we look at this curve, we would see that it is not very smooth all the time. Sometimes we would see a curve which looks like this. Then we can see that there is a point where we saw a significant amount of drop in WCSS, and then afterwards there was not much. So that could be a good data point for us to take as the number of clusters, and in this case it could probably be 3. This is called the elbow of this curve, and based on this method of finding the right number of clusters is called elbow method. Now a quick recap of the steps here again. We start with the number of clusters. Initially we have no idea, hence we take as many number of possible clusters one after another to see what is the right elbow. The second step is that we initialize the centroids for any 3 data points we want. The third step is that based on the centroid, we calculate the distance of each data point from that centroid, and based on that we assign the clusters. The fourth step is that we move the centroid to the average value of all the data points within that cluster, and we'll keep doing this back and forth till the centroids do not move anymore. And once they do move, we know that the solution has converged. And then again we change the number of clusters and we redo all of this, and at every stage we keep calculating within clusters sum of squares to see that how the error is dropping as we are creating more and more clusters. And based on the elbow method, we find what is the right number of clusters to be used, and then we use that for the final model which we build in the production. I hope this explanation was useful and intuitive. As I said, I tried to keep the math minimum and focused much more on the intuition behind these algorithms If you want to see more of these algorithms explained in a similar way, please let me know in the comments below what algorithm you want me to explain, and I'll try my best to create a video for that. Thank you so much for watching.